Okay, this is making the point that if we change the time or space, we have to change the mean. In fact, we had a previous question where we did this before. The difference here is that we never ever use the one for which the mean is 0.2. This model here, where the mean is 0.2, is the number of daisies per square metre. Oh, so incidentally, they tell me it's a poisson anyway, but this is why it's poisson. We're counting the number of daisies in a fixed space, okay? But the fixed space we're using is 100 square metres, so we have to go straight in with a rescaled mean. So I don't want lambda is 0.2. My lambda is 0.2 scaled up from 1 square metre to 100 square metres, so that's going to be a lambda of 20. So now I know that lambda is 20. I mean, you can take it from here. A probability of at least 25, and daisies in that range, dead easy. So for at least 25 daisies, want this, don't want these. Inclusion box has everything, exclusion box has this. So the subtraction is like this, so I need to do 1 minus, set it up with x is 24 and lambda is 20. Probability is that. 4, 3, 2, 3. Do the subtraction and you get the answer, which is 0.156. That's going to be to 4 significant figures. And in part B, always do the diagram. More than 10, so I can't be 10. Certainly can't be 9 or 0. Okay, I can be 11. I can be 19, but it's fewer than 20, so I can't actually be 20. So therefore, I need to do an inclusion box, which takes the 19, and an exclusion box like this. So the subtraction is... Always set up the subtraction you're going to do, because it's worth method marks in case you muck something up. So 19, we don't have to change lambda again. We're still dealing with the same time period. And we have got that probability. There it is. Change x to 10 on the calculator. Second probability. So here's our subtraction. I seem to be doing more decimal places than usual. Won't do any harm. Here it is on the calculator. And there's my answer, 0.3684. Double underline it, 4 significant figures should be fine. Okay, so without more ado, let's look at a more interesting one. So we've seen that we can just scale up a mean. Here we've got 3 different Poisson distributions. We've got a mean number of deaths per year, so fixed time or space, so we're counting events in a fixed time or space. Good, okay. Assuming it's independent and a constant average rate, we've got a mean of 3.8, so it's a Poisson with a mean of 3.8 for England, 0.8 mean for Scotland, and 0.5 for Wales. Okay, it tells me about independence at random, so yes, the conditions for a Poisson are met. So the probability of 7 or more deaths, but this now says on the British mainland, which means, okay, England plus Scotland plus Wales. Okay, I think we're ignoring Scottish Islands for this. Okay, so British mainland. So therefore, the total number, if this is X, the number in England, and the number in Scotland is Y, and the number in Wales is Z, then what I want to do is form W, which is the total number of deaths in England and Scotland and Wales, which is X plus Y plus Z. Now, the lovely thing about Poisson distributions is that they just add up beautifully. When you do this with normal distributions, you have to be a whole lot more careful. And you can't do it at all with binomial distributions. They don't add nicely at all. But the Poisson distribution works beautifully. W will have a Poisson distribution, so I should say twiddles, Poisson. Okay, and the mean of this Poisson is just going to be 3.8 plus 0.8 plus 0.5, which is the only parameter I need. So I get a new Poisson distribution, add these up, and you get 5.1, is it? There it is, I've done my twiddles properly. Okay, so the probability of 7 or more deaths, so I want, okay, don't be lazy, write the possible outcomes. So I want 7 or more. So I could have 7, I could have 8, I can't have 6, I can't have 0. Inclusion box includes everything. Exclusion box is there. So it's 1 minus the probability of x being less than or equal to 6. 1 minus, bang this on the calculator. Okay, so I've got an x of 6, I've got a lambda of, that's now 5.1, and hit the button, and it's this probability here, 74742. Do the subtraction, we get 0.25258. Oh, I've given it to 5 significant figures, aren't I lucky? Good. So, how easy do you want? Okay, about as easy as that, I should say.